So, hello everyone. We'll proceed further and we'll discuss today about mobility or degrees of freedom and its importance. So, suppose we have a body in space. Okay, let us draw it first. Let's say we have a body in space. In spatial coordinate x, y, and z. Say this is x, y, and z. So we say the body is free to move, then how many motions are possible? Let us imagine first. So the body can move and forth in x direction, and it can also rotate about the same direction, x axis. Same, it can move along y axis, and it can also rotate about the axis, and it can move along z axis so as it can rotate about z axis. So in total we can see here there are three translational motion and three rotational motions are possible. So if we are interested to completely restrict the motion of this body, then we have to restrict all these 6 variables. Okay, so this is known as actually degrees of freedom. So generally it is defined as the number of independent coordinates to completely constrain the motion of a body. In short, we used to refer this as DOF, degrees of freedom. It is also known as your mobility. Okay. Now, examples if we take, so a body in space, as we discussed now, it will have 6 degrees of freedom. If we say a point in space, then it will have 3 degrees of freedom, because let's say in x, y, and z coordinates, we have a point somewhere at x1, y1, and z1 coordinate. We if we are telling that rotation of a point, it is not practically decent. Okay, so we can only move the point from one coordinate to another one. So that's why 3 translational motions are possible. Okay, it can move from x1 towards x2, and also towards y2, then towards z2. Okay, so it can come somewhere here, like this. So its degrees of freedom is 3. Similarly, suppose we have in a planar case, okay, only x and y, planar case, and we have 2 links. Let's say this is link 1 This is link 2. Let's say link 1 and link 2. Now let's say link 1 is at an angle with theta 1 with x, and link 2 is at an angle theta 2 with link 1. That means it is at an angle in total theta 1 plus theta 2 with x coordinate. So if at all we are interested and now suppose the current position is at x1 y1, and we are interested to move this end point to somewhere here, to somewhere new point x2 y2, and if we restrict these two variables theta 1 theta 2 completely, then the tip cannot move to this new position. Okay, its motion is completely restricted. So its degrees of freedom its degrees of freedom is 2 in planar case. Okay, likewise further some important aspects are if we increase let's say the body has more number of degrees of freedom than required, then we call this as a redundant body. Okay, if we further increase its degrees of freedom, if we further increase the degrees of freedom, it becomes a hyper redundant system, you can say. Okay, and further if we increase in DOF, will let this body to become a continuous system. Okay, for example, if we say all of you might have seen one elephant trunk. Okay, it is somewhere like this. Okay, having a number of ring muscles. Okay, because of these muscles the elephant is able to move in any direction. Okay, it's able to move its trunk in any direction. So it's a case of a continuous system. Okay, it's a case of continuous system. Now from dynamics point of view, if we discuss what is degrees of freedom, just now we discussed that an unconstrained rigid body, an unconstrained rigid body in space has 6 degrees of freedom. How? 3 translational, and 3 rotational. So The connection of a link with another, the connection of a link with another imposes certain constraints, certain constraints on their relative motion, okay. The number of constraints, or we also call them as restraints, can never be zero, okay, can never be zero. Means for our mechanism point of view, if you say the rigid body cannot be completely free from all constants, okay. At least one link will be fixed or some conditions will be there. So in other words, we cannot say that a zero order system, okay, you can say zero order system is not possible. Okay. Now the number of constants can never be 6 also. The number of constants can never be 6 also, okay. If it becomes 6, then it will react as a solid body, okay. When all the joints become solid, this condition happens, okay. But from mechanism point of view, it is not possible. So it may be a one order system, it may be a second order system, okay. We can call this as first order system, second order system, third order system, fourth order system, and fifth order system, okay. These are the possibilities, okay. It cannot be 0, it cannot be a 6th order system, okay. Now if we are saying first order system, that means it will have one constant. A second order system means it will have two constants. Third order system, likewise, it will have three constants, okay, likewise, okay. So here it will be 4 constants, here there will be 5 constants. Fine. Now how to find out the mobility? So you can say degrees of freedom, or in short we may write capital DOF or small DOF of a pair is defined as the number of independent motions both translational and rotational, So in short we can say degrees of freedom is equal to 6 minus number of restraints. Why 6? Because if you are telling about a free body out of free from all constraints or restraints, then its degrees of freedom is 6, but practically it is not possible. Then we'll minus what are the number of constraints we are imposing, then that will give us the available degrees of freedom of that system. Okay, that is why 6 minus the number of restraints. Okay, now suppose let's say let n is the total number of links in a mechanism, and f is the degree of freedom of the mechanism, and P1 is the number of pairs having 1 degrees of freedom, P2 number of pairs having 2 degrees of freedom, likewise P3, P4 and P5. Okay. So it is having 3 degrees of freedom, it is having 4 degrees of freedom, it is having 5 degrees of freedom. We cannot say P6 because it will be if it is having 6 degrees of freedom, it is practically not possible. Okay, these are basically the joints. Okay, now in a mechanism, generally one link is fixed always. Okay, so the number of movable links will be equal to n minus 1 always. Okay, now if a pair having suppose P1 is having 1 degrees of freedom, that means in other sense it will impose 5 constants, or you can say restraints, isn't it? So similarly, if we are having P2 having 2 degrees of freedom, it will impose 4 constants. P3, which is having 3 degrees of freedom, will impose 3 constants. Okay. P4 having 4 degrees of freedom will impose 2 constants. P5 having 5 degrees of freedom, means 5 way it is free, so it is fixed in one way only, one constant is there. Okay, so now if we need to find out the total available degrees of freedom in that mechanism, how to find? Let's say F is the total number of degrees of freedom, then 6 is the maximum degree of freedom that we can have, but it is not possible because at least one link is to be fixed, so n minus 1, this is the degrees of freedom. Now we have to minus all the total number of constants from these degrees of freedom. How to do that? Let's say if we are talking about P1 is imposing 5 restraints, so minus 5P1. Then similarly it will be 4P2 minus 3P3 minus 2P4 minus P5. So this is a generalized form of equation to find out the number of degrees of freedom in a mechanism. Okay, is in this equation. Let's say this is equation 1. Okay, now this equation 1, okay, this equation 1 is known as Kutzbach's criteria. It is called Kutzbach's criteria. Now what you see in most cases, you will find mechanisms subjected to planar conditions. Okay, 2-dimensional. So mechanisms in 2D cases, for example, if you see 4-bar link mechanism, slider crank mechanism, etc. These are treated as 2D mechanism, okay, in which the displacement is possible along 2 axes. Okay, here in this case displacement is possible along 2 axes, and that means one restraint here and rotation is possible about only one axis. That means another two are restraints. Okay, two restraints. So in general there are maximum 3 degrees of freedom. So in this case degrees of freedom can be defined as f is equal to 3 multiply with number of movable links into n minus 1 minus 2p1, okay, minus p2. Now this equation is used for planar condition or two-dimensional condition mechanism. This is equation 2. Equation 2 is termed as Grubler's criteria. Okay. It is called as Grubler's criteria. Okay. So using these two equations you can find the degrees of freedom of any system. Now what is kinematic chain? If somebody asks what is kinematic chain, kinematic chain, when the kinematic pairs are coupled, kinematic pairs are coupled in such a way that the last link is connected to the first one, it is called a kinematic chain, and it transmits a definite motion. For example, we say a 4-bar chain. Okay, if I draw a 4-bar chain, let's say its one link is fixed. Okay, because as per our criteria we have to fix one link, which is known as linkage. Fixing one link is known as linkage. There should be a linkage in the mechanism. Okay, let's say this is link 1, then this is link 2, then so this is link 3, this is the joint, then we have this is link 4, this is the joint. Okay, so here you can see the first link, that is the link 1, is connected with the last link, and they have a particular motion to transmit the relative motion. Okay, so it is known as a kinematic chain. Okay, this 4-bar chain is an example of a kinematic chain. Okay, that's it, and in the forthcoming classes we'll be discussing few examples of the different types of degrees of freedom available in different conditions. Okay, and we'll proceed further to inversions of mechanism. By fixing different links we can get different mechanism out of it, so it is known as inversion. Okay, that's it for now. Thank you.